recorded, I guess it is. You know, I don't know, we're recording this, and I don't know the laws about recording people that that don't have your permission. I know in the state of Texas, it's okay to go in with an audio recording into a room. And as long as you are controlling the audio recording, you can record anything that you want to. But that isn't true in all states. I don't know how that extends when you have a Zoom conversation. So anyway, that's one of the reasons that Zoom asks when I do the recording, asks if it's okay if you're recorded. So it's kind of giving me the permission to do the recording. Now, I know most of you guys, let's go around and before I get into some of the things, kind of introduce ourselves. I think that what would be fun, I always like to hear something about you that nobody would expect. Now, if you've been in a class before and you've said that, don't repeat what you said before, repeat something new. And if you can't think of anything exciting about yourself, make something up, okay? And then I'd like you to tell you, I'd like to ask who you work for, and I don't know, let's just leave it at that. Maybe if you have a good joke, you could share with us. That would be good, a good short joke. So let's start from right to left, and we're being joined by Theo. Theo's logging on twice.
My computer crashed, so I'm rebooting it. So I hopped in on my iPad.
Okay. Well, that sounds good. So let's go ahead and start from left to right. Theo, do you want to tell people your name, who you work for, something, maybe what your research is, and then I don't know, then your favorite ice cream.
Okay. All right. So my name is Theo Steinby. I'm a first semester, or now second semester PhD student here at Baylor, working with Dr. Kojal, and he does research in neuromorphic computing. And so I'm just kind of starting in that. But right now our project is to take something called an event camera, which is a neuromorphic inspired imager, and to try and put that through a stochastic computing image recognition network that was developed by Matt Carano, who's a master's student here at Baylor, and to try and use that whole combination to do image recognition. I've worked for Sandia National Labs for the last 3 years in a couple of different areas there. But most recently, it's been the cluster computing team. As well as I've done kind of some modeling with radar, and then also some embedded software. So I've been there for 3 years, so I've gotten to move around a little bit. And then
tell me what cluster computing is. What do you do when you cluster?
So it's the hot term is supercomputing, but basically they have, some of them have tens of thousands of servers that have a significant number of cores, and they're all tied together on a network. And most of the computers or the servers on the network don't have hard drives in them, and so they're all booted over the network. And you have a software stack that ties them together to allow a single job to run across multiple servers. And that's how they try to speed up a problem, is just by throwing lots of parallel processing at it.
And so you got to do your programming like it was a parallel computer, I suspect, right?
Yes, sir. And then most of what I have done has been learning the software stack. So I've built like 3 different standalone clusters that use the same software stack as the large systems do. So.
Okay, that's interesting. Okay, now something weird about yourself.
Something weird about myself. Let's go with, I have a manual transmission car, and it was not intended to be my car, but my sisters, who it was actually bought for, decided that they didn't want to learn how to drive stick shift, and decided it was intimidating to them. So that's how I got my car. And oddly enough, the catalytic converter was stolen yesterday morning, which is why I'm not at the brick.
Why would somebody steal your catalytic converter?
Apparently, they have some catalytic converters have rare earth metals in them, and so apparently they can be somewhat valuable on the black market. Certain types.
They use platinum.
They use them what in Adam?
Use platinum.
Platinum.
Mm-hmm.
Okay. So, boy, that's fascinating.
It's unfortunate.
Okay. I know in Europe they have a lot of stick shifts, or at least they used to. Yeah. And here, I think everybody in America almost drives an automatic anymore. Glauco, did they have a lot of automatics or mostly stick shifts in Spain?
Mostly that thing that it cannot be deaf. Yeah, I have a stick shift car in Spain. I have one.
You do? Okay.
Yeah, we all have them. Only some automatics, but not very much.
Okay, Adam, Justin, can you drive 4 on the floor?
No, I've never tried to drive stick before now.
Okay.
I've tried it in a field and did okay with it, but haven't actually took it on roads.
You never took it on a road. I remember my father was teaching me to drive a stick, and you jam it in there and you hear all this crunching, and he used to say, "Grind me a pound too," because it sounded like a grinder that was grinding up meat or something like that. So, okay, thank you, Theo. Appreciate it. Okay, Glauco, you're going to really have to dig deep because I know a lot about you.
That's my intention to. Okay. Maybe you know it all, but probably you don't remember it also.
Okay, that can be true.
That's my goal. So I'm going to start by the easy things. My name is Glauco Amigo, as the screen is written. I'm from Europe, and I came to Baylor on 2019 to start working with Dr. Marx in information theory and also artificial intelligence. What else? I'm a second year PhD student. My favorite ice cream is Häagen-Dazs because it resembles me to a homemade ice cream my mother did when we were children. We had this household ice cream machine, and it didn't work very well, but it was very tasty and natural. It's the same flavor as Häagen-Dazs.
That's interesting. Theo, we let you get by without your favorite ice cream. What do you say?
We did. I say I would go with vanilla. My family had like this chocolate sauce that my grandparents always made, and so it's vanilla and chocolate sauce.
Very good. Okay, Glauco, something weird about yourself that I don't know about that you can make public.
So I'm going to tell all my history in academia and work. So probably even if you know, it's going to be surprising somehow for you too. So when I finished high school, I started math, a math degree. On the second year, I decided to be a pianist. So I focused on music school. I was like a couple of years, 2 or 3 years, playing piano and teaching. And then I have a lesion in my wrist, so I changed careers. So I studied social work because at church we had some centers for minors, and they told me about that. So I did that. Then I finished the degree. I worked for 3 years in centers for minors. And then 3 years later, I decided to study computer science in Spain. And then I worked for a couple of years as a software engineer in a factory for electronics, but I was in the IT department. And then I came here. So probably there is something there.
So, okay. So of all of the things you've done, what's your favorite? I shouldn't ask that. Wow. What's your second favorite? I know what your favorite is. Your favorite thing here, right?
Okay. So my second favorite, yeah, I think my favorite's been here with the PhD. And my second favorite was the computer science degree, I think.
Oh, okay.
Yeah.
Wow, you're a student now.
I can say.
Go ahead.
I can say that when I was a child that I started studying music, it was for playing at church, and even when I'm not a professional pianist, I used to play in worship. So
okay,
that did the trick.
Now I, as you know, am full of trivia. And the reason I'm full of trivia is because books like this. This is called Uncle John's Bathroom Reader. And it's a very thick book. It's a very, very thick book, but it contains stories about long enough to read during a trip to the bathroom. And one of the things I learned about Haagen-Dazs is that Haagen-Dazs, what do you think the origin of the word Haagen-Dazs is?
German?
No,
No.
It was made up by a couple of Jewish guys in New York City that wanted a cool name to put on their ice cream.
So they put the umlaut.
They put
there.
the umlaut over the A. Now, in German, do umlauts go over the A?
I should know, O's, but I don't remember.
Yeah, I'm not sure that they go over the
over the A they go. Yeah,
they go over the A's. Okay,
like Handel, the composer Handel.
Oh, is he a umlaut A?
Yeah, you can write EA, E, or with the umlaut. Yes.
With the umlaut. Okay. Anyway, it has nothing to do with the origin of the ice cream. The ice cream was made in New York and named by a couple of entrepreneurs that wanted a cool name, and clearly it stuck.
Yes.
It was just wonderful. So anyway,
that explains that it's cheaper here than in Europe. It was traveling for me, thinking, how can it be cheaper here if they import it from Germany?
But they don't. Yeah,
that makes sense.
New York. Okay. Well, it's a small. So if you want to keep up on your trivia, get yourself a copy of Uncle John's Bathroom Reader. There's about 20 volumes out there. So. They're really, really fun. It's amazing. Okay, Adam.
Yes, I am Adam Goad, a second-year PhD student here at Baylor. Did my undergrad here as well, so I've been here a long time. I work with Dr. Bayless, doing algorithms to control adaptive RF hardware. Currently focusing on array-based systems and the interactions between 5G and radiometers. A fun fact about me. So my middle name is Clarence, but until I was about 11 years old, I thought it was Clearance, because one time, like when I was real little and had just found out I had a middle name, I was at the store with my mom and I saw a sign that said Clearance, and I was like, "Look, Mom, a sign with my name on it." And she wasn't really paying attention to me, so she just said yes. And then later I was like, "Oh, what's my middle name?" "Oh yeah, that sign." And then I knew that sign said Clearance, so I thought my middle name was Clearance.
Adam, that's really funny. I know something I can tease you with now. As we call you Clarence. Okay, really good. Okay, Justin.
Yeah, so my name is Justin. I'm a first-year master's student, and I've been trying to develop a fast impedance tuner as well as applications for spectrum sharing and that kind of stuff. But lately trying to work on waveform optimizations and beam pattern optimizations. And my favorite ice cream would have to be vanilla as well, especially with some chocolate chip cookies. It's the best thing. Something interesting about me, I guess, would be that I love to eat garlic with just about anything.
Garlic?
Yeah, like where you just like minced garlic and different kinds of like garlic you can just add in a seasoning.
There is a restaurant that I went to around Pasadena, California called the Stinking Rose. And in the Stinking Rose, all of their dishes are made with the Stinking Rose, which of course is garlic. And for dessert, yes, they had garlic ice cream. If you ever had garlic ice cream, they had it though. They had it at the restaurant,
I haven't had that.
And it wasn't that bad. I mean, it was very different. But garlic ice cream was something they had at the Stinking Rose. I always thought that would make a great franchise, but I don't even know if the restaurant's still open or whether they're franchised at different places. So that's really interesting. Well, fascinating. Thank you, Justin. My name is Bob Marks. I'm your humble instructor. I have been at Baylor since 2003. I was 26 years before that at the University of Washington in Seattle. I came here because Baylor was a research university, and that was God's gift to me. I think all of you have a God-given intellect that is above normal. Otherwise, you wouldn't be in graduate school. So that's one of God's gifts to you, and I have that gift also. And anyway, Baylor was someplace where I could do research and celebrate the Lordship of Christ. The most important thing in my life is my relationship with Jesus Christ. And I hope that it shapes all of the things I do. And I hope that people see, and I hope that you see in my dealing with you, that I am indeed a follower of Christ. Let's see, my specialty, I do all sorts of things. I'm working with Dr. Bayless and Adam and Justin and Glauco. Maybe you someday, Theo. I work with a lot of professors because when I came here, there was really no research going on. And one of my jobs was to kind of bootstrap research in the department. And so there was a time that I published with about, I don't know, 30, not 30, because there weren't 30 people in the department. Anyway, way over 2/3 of the faculty in the department. So I came in and started doing joint research. So I published with, of course, Dr. Bayless and Dr. Jean. Haven't published with Dr. Kozel, although we've talked about a lot of interesting stuff. I've submitted proposals with Jonathan Hu and I don't know, some people that have left Baylor. So that was my calling. So I spent a lot of time working with other professors, hopefully helping them with their research. My specialty, if you've seen my classes and my work, is primarily in the area of mathematics, algorithms, artificial intelligence, things of that sort. So what I am good at is bringing to the table these sort of mathy things, hopefully to complement the expertise of other professors. Dr. Bayless is just a whiz at microwave circuits. And I am able to come in and learn some of the problems there and hopefully to help solve them. So that's what I've been doing. Something you might not recognize about me is I'm a musician. In the sense I'm a songwriter. In fact, when I went to college, I wanted to be a songwriter so bad, I just about dropped out of school to become a songwriter. And I've written many, many songs, and I'm a better songwriter than I am a musician. I wrote all of the music for my wedding. I've written songs for all of my kids and most of my grandkids. They keep coming though. I still got a pair of twins I need to write a song about. But yeah, I'm usually very proud of them. I do a podcast, which I know that Adam listens to every once in a while. And the music in there it's an example of one of my compositions. So the music in Mind Matters it has words, and it's called From Mud to Guppies. And it's the story about the creation of life from mud to the first life, which is guppies. And it has words and things of that sort. So that's probably what you don't know about me. Well, with that, let's go ahead and get started. We are at Baylor. Despite the things going on in our country, we still have the ability to pray here. So I'd like to open our class with a quick prayer. Father God Almighty, we come to you in thanksgiving. I thank you for these 4 gentlemen who are taking the course right now. And I pray, Lord, that you make me an effective instructor that is respondent to their questions. I pray, Lord, that you open up their intellect so that they're able to absorb things. Bless them all in the research that they do. And let them keep in mind, Lord, that it is not the gain of power or influence that is important, but it's the glorification of you and the advancement of your kingdom. We love you, God. It is such an honor to talk to you, the creator of the universe. It blows my mind every time I spend time in prayer. The creator of the universe, I'm allowed to talk to because of your son, Jesus. That's truly amazing. You are an amazing God, and we thank you for being amazing. And we pray these things in Christ's name. Amen. Okay, guys, let's go ahead and get started. And I wanted to share the screen. And that's exactly what I'm going to do. And we'll see what pops up in the screen here. Okay, one of the things is that there is a spreadsheet. And did I send this to you at all? Okay, I sent you this spreadsheet. This is where you're going to go for homework assignments, resources, and things of that sort. Everything is available on the web. We have slides, and I'm going to be going through slides. One of the things is that I have taught this course before, and every time I teach the course, I update the slides, so new things happen. So if you download the slides before I lecture on them, it could be that they're outdated because I might give some updates through them. But here is a HTML, a link to where you can get these slides. They're in a PowerPoint. We do have a syllabus, and let me bring that up. Okay, whoops, okay, there we go. Here's a syllabus. Now, you can go through this if you'd like, and you'll find out that this basically covers the different things that I'm going to be talking about. Let me just review the numbers. We're going to have a review of probability. I know that you all have had probability and have had some background in it, but I think it's important to review it, and we are going to do that. And we will go through the fundamentals, which is a review. We will talk about random variables and exactly what a random variable is and its importance. It turns out no matter what field you go into in electrical and computer engineering, no matter what field, you are going to be using probability and stochastic processes. And so we will talk about random variables and about some of the different random variables. Then we'll talk about transformations of random variables, which I'm sure is a new topic for you. This is a topic, for example, if you are measuring say an electric field, and that electric field is a random variable with a Gaussian distribution, but you don't take the actual electric field measured in, say, volts. You don't measure it in volts. What you do is you typically convert it to dB, right? You take the log base 10 of the volts divided by some reference point, and that's called dB. So the question is, if your original random variable is a Gaussian random variable, what does your random variable become when you express it in dB? It's no longer Gaussian. So what is it? That's referred to as a transformation of a random variable. Another simple example is if you have a current, a stochastic current that is going through a resistor, and you're not interested in the current. Maybe the current has a Gaussian or some sort of distribution, but you're interested in the power which is dissipated by the resistor, which is proportional to the magnitude squared of that current. And if you have the distribution for the current, how can it be, how do you obtain the distribution of the magnitude squared of the power? The distribution is indeed changed. So again, how do we do that? Okay, I'm dinking around with stuff here. I still haven't mastered Zoom. I've been on a million Zoom calls and I still haven't mastered it yet. Oh, well, I'll worry about that later. So transformation on a random variable. Then we'll talk about a little bit about information and entropy. There is a course offered at Baylor, which I teach, which is called Introduction to Information Theory. And this Introduction to Information Theory is the foundation for all communications today. It turns out in 1948, a guy named Claude Shannon wrote this incredibly beautiful paper, and he established the mathematics of communication. And his results are something that we use today on our cell phones. He showed that over a noisy channel, you could communicate with arbitrarily small error. And this is a foundationally important thing. Information theory is tied directly to probability. In fact, it's measuring something in coin flips. For example, if you flip a coin and you want to get 10 heads in a row, what's the probability of that? the probability of that is 1 divided by 2 to the 10th, which is about 1 over 1,000. So that's the probability. It's easier to talk about that probability, 1 over 1,000, in terms of the number of bits. Each coin flip gives you 1 bit, and you obtain that bit by taking the log of the probability. And the log of 2 to the 10th is log base 2 of 10 to the 10th is 10 bits. And so we can think of that probability as either a probability, the probability of getting 10 heads in a row, and talk about that probability being 1 chance in 1,000. Or we can talk about it and say this is 10 bits of information, which is exactly the same thing. And sometimes it's easier to interpret probability in terms of bits than it is with, with other than probability. Say, I say that the chance of something happened is 1 chance in 10 to the 80th. You sit there and you go, but what's the difference between that and 1 chance in, say, 10 to the 70th? I have no intuitive comprehension of that. But if I say that that corresponds to a number of bits, let's see, say 1, yeah. Let me get this right. Okay, say 1 chance in a billion. What does that mean? Well, that's about the same as flipping a coin 30 times and getting 30 heads in a row. So 1 chance in a billion, if I've done it right. Yeah, 1 chance in a billion is about the same as 30 bits of information, flipping a coin 30 times and getting heads all at the same time. So it's another way of thinking about probability. At least that's one of the paradigms that you can look at. It's much more important than that, but that's where we're going to talk about. So we'll talk a little bit about entropy. Then we're going to talk about two-dimensional random variables, because many times random variables are related to each other. We'll talk about 2 different random variables, and this leads us into multiple random variables. This reminds me of a backward tribe that could only count to 2, and they went 1, 2, and they couldn't comprehend above 2, so they went many, right? And so we'll talk about multiple random variables, because we could spend a lot of time talking about 3 random variables and 4 random variables, etc. But if you extend the concept of multiple random variables, which is number 5, you get number 6, which is sums of random variables. Okay, we'll talk about that. And maybe one of the most important theorems in mathematics, or at least one of the most powerful, which is something called the central limit theorem. Central limit theorem says, and this is fascinating, it's more of a math result than it is a probability result. If you take any functions and you convolve them with themselves, you're all electrical engineers, you know what convolution is. But if you take like 500 different rectangles and you convolve them with themselves, guess what you get? You get a Gaussian. And if you take a bunch of weird functions, little squiggles and humps and uniforms, and you convolve them together, you get a Gaussian. Gaussians are really, really curious. And you'll notice if you have a rectangle and you convolve it with itself, what do you get? You get a triangle, right? If you convolve a triangle with a rectangle, what do you get? You get something which is piecewise quadratic, and it's already starting to look like a Gaussian, isn't it? And so that's very interesting. I think that that's just a fascinating idea, that if you add numbers together, that you do get Gaussians. And what do we do when we take averages? We add a bunch of random variables together and then divide by n to get the average. And that random variable is probably going to be a Gaussian. It doesn't matter what the underlying distribution is. So it's a very powerful concept. Then we'll talk about stochastic processes. Stochastic processes are kind of like an infinite number of random variables. So we go 1, 2, many, infinite number. And we're all familiar with stochastic processes in the terms of noise. And we've all heard terms like white noise and pink noise. And we'll talk about some of those different characterizations of noise and how we can characterize noise. And this is going to be important in all engineering designs. You have to worry about effects of noise and uncertainty. It's just a fundamental result. And then lastly, we'll talk about, well, 2 things. We will talk about stationarity. That's a type of stochastic process, very important. Ergodicity, I love that word. If you haven't heard it before, ergodicity is a really cool word because it means that you are able to characterize the statistics of a random variable by looking at a single realization of them. We'll get to that. And then we'll talk about processing of random variables. What happens if you, or of random signals? What happens if you take a white Gaussian noise and you put it through a low pass filter? What's going to be the output? It's no longer white Gaussian noise. It's kind of like a transformation on a random variable, right? So if you take white noise and you put it through a low pass filter, what is the corresponding distribution of the output of that low pass filter? So that would be under filtering stochastic processes. Before that is defining the idea of power spectral density. I know of those of you that work with Dr. Bayless know what a power spectral density is. But how do we define it? How do we define it in terms of a stochastic process? We will get into that definition and understand exactly where the concept of the power spectral density comes into play. And it's kind of remarkable, the relationship between the power spectral density and the autocorrelation of the stochastic process is one of those things that you look at and you go, wow, I wouldn't have expected that. So we'll see that once we get to the processing of random signals. And that should be about it. We might not hit all of these. And I might deviate from this a little bit, but that's the way I teach. So I would suggest that as you begin to look at and study for the course, that you go primarily by my lecture notes and then the problems that I assign you. And if you do that and leave the text, this is the text, Alberto Leon Garcia, Probability Statistics and Random Processes for Electrical Engineers. And this is a really great text, by the way. The form of this text goes back to 1965 and the first really great engineering book on probability and random processes published, which was by a guy he was from New York. His name was Athanasius Popoulas. And what Popoulas did is he didn't want to get into the rigor of the mathematicians. Mathematicians, when they talk about random variables, they talk about all of these axioms, and then you derive a theorem, and then you derive a lemma. And if you get a bad lemma, what do you do with a bad lemma? This is a joke, guys. You should get it right away.
Make lemonade?
Make lemonade, that's right. Okay, that's what you do with the bad lemma. Okay, so you get all this stuff and you progress slowly throughout the mathematics and you develop it to such a degree that you're looking so closely that you no longer see the big picture. What Popoulas did in 65 is he said, look, we don't have to go down to that rigor. We have to be able to develop the mathematics, of course, but we don't need to go down to that level of rigor. So he did a balance, and this was a balance between rigor and understandability that was really, really effective. And a number of people, including Garcia, have adopted Popoulas's style. And so this is a very good book, and is one I would recommend to you. If the other thing is that, as I mentioned, there is a Google spreadsheet, and all of you need to bookmark this page, because I will be using this Google spreadsheet throughout. For example, you will have links to the slides that I present. You will have links to the syllabus that I presented. Here's a link to the text on Amazon.com. And even I self-linked myself. I don't know why I did this, but this is a link to this page, okay? And we will talk about each one of the titles. I'll assign homework here. It'll either be from the slides, and the homework will be the results here and the due date. One of the things that I like to do in class is I like to motivate you to look at the homework. And I think if you just do it and hand it in, that's okay. But I'd like you to have an understanding. So if you've had me before for classes, you know what we do. We get to a point, and then what I'll do is I'll flip a coin, and I'll ask one of you to go over your solution to a problem. Now, to do that, to go over the solution to the problem, you'll either need one of these pads, which you can write on a screen with, or probably better yet, have your homework worked out and available in an electronic form where you can share your screen. So that's going to be something that you need to do, because you're going to be presenting to the class these problems. So the examinations will be oral. I suspect that currently we'll have 2 exams, 1 midterm, 1 final examination. And I will be providing a box link where you can upload your solutions to a place in Box where I can take a look at them and get an idea of how you're doing on the homework. But I also want you to be responsible for giving those in class. Is that okay? So I haven't done the box link yet, but I will be doing it. And as soon as I do it, we'll go on to this page. So make sure that you bookmark this page, because during this course, we'll be going through it a lot. Okay. Okay. A few introductory remarks. You know, this is very interesting. Everybody thinks they understand what random is. This is a Dilbert cartoon. It says over here we have a random number generator. It's 9999999. Are you sure that's random? Well, that's the problem using randomness. You can never be sure, because there is a probability that it could be 999999, right? There is a finite chance. But we all think we know what probability is, and we all think we know what randomness is. We think about flipping a coin or throwing a die or something like that. But I tell you, it's much deeper than that philosophically. If you take the course in information theory, you'll find out that there is a totally different approach of randomness, which is, you're all familiar with zip files, right? If you had a sequence of 1s and 0s and that did not zip, you could not compress it, then that would be random. Whereas if you had a sequence of 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, that would zip to a very small file, right? Or 0, 1, 0, 1, 0, 1, that would zip to a very small file. But if you just had random numbers from coin flips, say 1 million of them, they would have a difficult time compressing in general. So that's another definition of randomness. We're not going to appeal to that concept of randomness here. You also know that on computers, you have so-called random number generators. Do you know that a computer can do nothing stochastic? A computer can do nothing random. All of the computer code that you are used to uses so-called, let's see, what's the word? Pseudo random number generators. They are deterministic. And if you can crack that deterministic code, by the way, if you can crack that deterministic code, you can actually figure out what the future random numbers are going to be. In fact, there's an argument, and I subscribe to this. It is philosophical. It is ideological, I suppose, that the only true randomness that exists in the universe is from a quantum collapse, because you have no idea where that quantum collapse is going to come from. And so you can't do it with pseudo random number generators. You can't even do it with a coin flip, because you can argue that with a coin flip that you have all the physics going for you. You know, if you know all the details about the air, you know the mechanics of the flip, you know the mechanics of how the coin is going to land and bounce, then it's totally deterministic. But it turns out it's so complicated that we find out that the model, and this is what probability is, it's a model, that the model of the process is stochastic. Now, you might not think that a coin is, I want to do this experiment one day, but suppose that you had a big coin like this, and you put it on your desk and you went, thump, and you always had it with heads pointed up the first time. Do you think if you didn't hit it that hard, you'd get more results on one side than another? I think you might, if you had a really, really big coin and it only had time to maybe flip once or twice. You could literally control it so it only flipped once, and you always got the same results. So it's a matter of scale. We don't use coins this big, we use coins this big. And so again, the idea is the probability is a model. It's an incredibly useful model, and is one that we're going to be studying in the course. This is something of history. I noticed that there's lots of references to stochastic processes in the Bible. In fact, was it Gideon who put out a fleece and said, God, if it's wet in the morning, I'll do one thing. If it's not wet in the morning, I'll do another thing. In fact, they call it casting a fleece. Now, he didn't look at this as a probability. He looked at this as a sign from God. But there's other places in scripture where they talk about casting lots, which is the understanding that if you did cast a lot, that the future would be random in some sense. Leviticus, read the first one. Aaron shall cast lots for the 2 goats. Numbers, but the land shall be divided by lot, by random drawing. Joshua cast lots for them at Shiloh before the Lord. Proverbs, this is very interesting. The cast lot puts an end to strife and decides between the mighty ones. What do you think that means? I think it means that if you're in conflict with somebody and you get together and say, look, man, let's not fight anymore. Let's flip a coin and let's just see who wins. And so that's what it's talking about. The cast lots put an end to strife. It puts an end to the conflict that goes on. Of course, very famous when Christ was crucified, his executioners divided up his garments among themselves by casting lots. So it was again a problem. They were assuming that there was kind of an equal probability of the future. But all of these kind of assume that. And that's a very simplistic view of probability. And then, of course, when the betrayer of Christ, Judas, was cast out among the apostles, they needed another one. So they drew lots for the replacement. They did this by random chance. And that's where they got Matthias as the addition to the 11 apostles. So this is a very rudimentary understanding of probability historically. So we know it kind of was like that in the in the Old Testament days and the New Testament days, in fact. But the founding of probability is due to these 2 guys. You've heard of them, Blaise Pascal and Fermat. And there's a great book, if you ever want some good recreational reading as far as the history of mathematics, get this book, Kevin Devlin, and it's called The Unfinished Game. And we'll find out why probability was founded by the unfinished game in a second or two. But the idea, the foundation here was that before Pascal and Fermat did their correspondence, this is a quote from the book. In the early 17th century, the outcome of something as simple as a dice roll was considered in the realm of the unknowable chance. Mathematicians largely agreed that it was impossible to predict the probability of an occurrence. Then in 1654, Blaise Pascal wrote to Pierre de Fermat, explaining that he had discovered how to calculate risk. The 2 collaborated to develop what is now known as the probability theory, a concept that allows us to think rationally about decisions and events. So in a sequence of letters back and forth, Pascal and Fermat developed the basic idea of probability theory. And Devlin points out that after this, and after there was an understanding of probability, that there were businesses which began to arise in terms of actuaries. You know what an actuary is? It kind of predicts when people are going to die. They also began to develop insurance. Insurance sellers could do insurance because they had this concept about forecasting the future. And of course, on the negative side, casinos began to open. They recognized that these laws of probability could be used to their advantage in order to make big bucks. So before 1654, before these letters, none of those events occurred. And when I first saw this, I thought, man, that is really hard to believe, because for us today, the idea of probability is so ingrained and so dominant in our thinking that it's hard not to think of it. So that's a little bit of history. So here's the game that they proposed. And as one of your first homework assignments, I'm going to ask that you solve this problem. We're going to solve the problem that Fermat and Pascal were working on, and it took them a long time to figure it out. Hopefully you can figure it out quickly. Who has heard of Fermat? What is Fermat famous for?
His last theorem, if I remember correctly.
You're right. His last theorem, which was solved by, oh boy, I forget the guy's name. But yeah, Fermat's last theorem. And the reason it was called the last theorem is because Fermat, in his books, used to write things in the margin. And in one of his works, the last thing that was written in the margin was a solution to this problem. Let's see if I can do it right here. Okay, it isn't doing it. Okay. He looked at this problem, and what he was assuming was that x and x, y, and z and n were all integers. And he asked, when does this have a solution? Now, we know that it has a solution for n is equal to 3. We know, for example, that 3 squared plus 4 squared is equal to 5 squared, right? So that's a classic 3, 4, 5 triangle, which, by the way, the Egyptians used to use. They needed 90 degrees. So they would measure out 3 units this way, 4 units this way, and they knew that if they did that, they would have a 90-degree triangle. So they could use that for measuring 90 degrees, which is kind of cool. Fermat said, I don't think that there exists a solution for this for n greater than 2. I think it doesn't exist for n is 3, n is 4, n is 5. I don't think that any of these other solutions exist. And in his column, he basically said, you know, I found a proof for this, but it's too long to include in this column. He said, I found a wonderful proof for this, and it's no longer in, but I can't write it down because it's too long for this column. Then, so this was an open problem for a number of years until it was solved by, could somebody Google that, Fermat's last theorem proof?
So Andrew Wiles.
Andrew Weil, yeah. And do you have the year? It was a decade or so ago.
I had it just a second ago. 1993.
Okay, 1993. Okay, so it was like 3 decades ago. Andrew Weil solved this problem, and it took him pages and pages and pages. It was a very thick, very, very thick proof. And mathematicians had to look at it. His first solution they found a flaw with, and he had to go back and correct it. But Andrew Weil won the Fields Medal. Now, the Fields Medal is the Nobel Prize for mathematics. It's only awarded once every 4 years, and I believe has to be rewarded to somebody under the age of 40 for some reason. So he got the Fields Medal for this, and this was one of the solutions of a problem which had been open for hundreds of years. So that's what Fermat was famous for. That's what this guy was famous for right here. He was famous for that. Blaise Pascal is a good friend of mine. He's a good friend of mine because I've spent a lot of time with him. I've read his bio. I've read his work. In mathematics and physics, what is he famous for? Do you know? What's the metric unit for pressure?
Yeah, you got the Pascal, yeah.
Is the Pascal. Yeah, the metric unit for pressure is Pascal. And one of the things Pascal tried to do was show that pressure decreases with elevation. And he would take, I think it was water, it might have been mercury or something, but he took some mercury, he turned it upside down so that there was a puddle of air at the top. And as he increased in elevation, this puddle of air got smaller and smaller and smaller and smaller. That's a reason today we talk about millimeters of mercury. And the reason that it got smaller and smaller and smaller was the pressure that was pushing the mercury up decreased. I'm sorry, it didn't get smaller. It got bigger, didn't it? It got bigger. Because the pressure pushing the mercury up got smaller and smaller and smaller. And so that gap got bigger and bigger and bigger. And so he did this. He did it at land level, and he climbed a mountain and he showed, yep, this principle worked. So he was a pioneer there. There is a there is a computer language known as Pascal. You know why? He invented, I believe when he was still a teenager, 16, something called the Pascaline. The Pascaline was one of the first mechanical computers. He did it for his dad, who was in some sort of business where he did a lot of work like accounting and stuff. So he made one of the first computers. It was basically a mechanical calculator a long time ago, and it was patented and sold for a while as a really great thing. But he did this when he was 13. In mathematics, I think we've heard of Pascal's triangle. You ever heard of Pascal's triangle? Okay, so that's named after him. He did a lot of work in I don't know, quadratics and binomial expansions and things of that sort. Very ingenious. One night in his life, which historians call the night of fire, he had been talked to, I believe, by his sister about Christ. And he had in his life something called the night of fire. When Pascal died, he looked, the undertaker noticed in his jacket was sewn some papers. And he looked at those papers, and what those papers contained were Pascal's notes of the night that he became a Christian. And you look at this, again, it's Pascal's night of fire, and you recognize that what an incredible experience that this man went through. And it changed his total life. He spent a lot of the rest of his life writing Christian apologetics. In fact, over at Truett Seminary, they currently study Pascal's Pensées, which is his book in apologetics. He began to write down all these notes of justifying his faith, apologetics, if you will. And he kept them, I guess, kind of in a notebox card, but he died before he could compile them together in a work. So his work was taken and transformed. And you can buy the Pensées today, the translation of it, on Amazon.com. And it contains a number of different, just profound theological observations. Something called Pascal's wager, if you've ever heard of that, which it's just what a nerd did. He did a Venn diagram of there is God, there is no God, you believe in God, and you don't believe in God. So that was the Venn diagram. And then he filled in all of the squares of the consequences of all these beliefs and showed that it was to everybody's advantage to believe in God. He also is, in my conversion to Christ, something I recognized. Pascal is famous for saying there's a God-shaped vacuum inside every man, which can only be filled through Jesus Christ. And I looked, when I was about your age, a junior in college, when I became a Christian, that described me and when I became a Christian. So Pascal was an incredible man. You know, when he died when he was 39. He did all of this work before the age of 39. Just a remarkable man. And as we see here, he's also one of the co-founders of probability. So what was the problem that puzzled Pascal, that he wrote to Fermat about? And in this book, by the way, they have the correspondence back and forth between Fermat and Pascal. Okay, they talked about something called the unfinished game. You can think of this as like in the playoffs, but here's the simple version in it. You have two people, and you call heads and I call tails, and you flip a coin 5 times. If 3 of them are heads, you win. If 3 of them are tails, I win. So the greatest winning of 3 out of 5. Does that make sense? So it's a very simple game. It reminds me of playoffs, right? The best of 5. The World Series is the best of 7. Whoever wins the best of 7. So this could be applied to this. So suppose that you had a side bet. Whoever won takes home $5,000. Do you get the idea? But what happens if the game is unfinished? For example, they flip a coin 5 times. Pascal has 2 wins and Fermat has 1. And then all of a sudden Fermat dies, so the game's over. How do you divide the $5,000? You get the question? This is the idea of the unfinished game which Pascal and Fermat played around with, whose solution was instrumental in finding the field of probability. So you're all thinking about it. I want you as a homework assignment to solve the unfinished problem with what you know. You're welcome to look at Google and different places, but I'd like you to understand that this problem does have a solution. It has a fair solution, and it has a solution that makes all the sense in the world. And the question is, what was that solution? So that's one of the homework problems I'd like to assign you. And that problem will be due next Tuesday. And I'll ask one of you to work the problem and tell us how it was solved. It isn't apparent right away, is it? Or is it? Does anybody have an idea how to do it? I know the solution, so I kind of know the approach.
I have one idea, but
okay, go ahead, shoot, Glauco.
I will check online. If we have one have 2 wins, another have 1 win, and 2 other rounds are unknown, so I will give 2,000 to one, 1,000 to the other, and the rest of it I will divide half and half.
Why? Oh, I see. That's not the answer.
Okay.
That's not the answer. But
Okay.
Good try.
Okay.
Now, see, the thing is that there's some outcomes that it's obvious. Like if they both had a single win, you divide the pot equally, right? Or if they both had 2 wins, you would divide the pot equally. But when the wins are asymmetric, when one is greater than the other, then you get into this problem of you got to think about it.
What if you just do it based on a percentage of current wins? So if Pascal gets 2/3 of the money because he has 2 of 3 wins.
No, that's not the solution either. So this is I don't think that's the solution. This is one of the problems wherein there is one obvious correct answer. And you can show that beyond a doubt. And so I'd like you to figure that out. That's a good head scratcher, I think, for next time. And so you'll be redoing what two of the greatest mathematicians at all time struggled with for a long time. But fortunately, you have the background to understand how to do this, and they didn't. This was new unplowed field. This was a new unplowed field. And like we saw before, these ideas and what happened there is something which nobody had ever thought about it. They thought the future was unknown, and it is unknown. But you can talk about it in terms of probability, and that's what they were doing. Whoops. Okay, so that's kind of some introductory material. Now I want to get into a little bit of the introductory material and a couple of problems that you might have heard of before. I'm not sure, but you might have heard of these before, and if you do, that's okay. So this is again the second set of slides, which is available on the web to you, and this is kind of a review of probability and random variables. There are different models of probability, and in fact, the unfinished game is a model of this. Is based on this first example. You look at an event, and you see the probability of the event. In the classical definition as the number of possible successes divided by the number of possible outcomes. We apply this all the time. A term we'll be using a lot in here is pips. Not a lot, but we'll use it. You know what a pip is? A pip is one of these little indentations on the die. So that right here on the top, we have 3 pips. Okay. So if you roll a die, what's the chance of getting 3 pips as the outcome? Well, there's only one way to get 3 pips, but there's 6 equally probable outcomes. So the number of possible successes divided by the number of possible outcomes is 1 out of 6. We use this concept all the time. And this is the classical definition. This assumes that we have the insight to analyze such a problem. And we always don't have that insight. Everybody here has played Monopoly, right? So we can ask ourselves, what is the probability of landing on free parking after 10 turns? Could we take the number of times that we land on free parking after 10 terms and 10 turns and then divide it by the number of ways that we don't? No, we can't do that. I think that's too complicated, right? So I think that applying a more difficult problem to this kind of classical definition is not possible. But many times our intuition is able to show these probabilities and show them very, very nicely. Here's one of the problems with the classical definition. This is something called Bertrand's Paradox. And it's something that I want to ask you about. And by the way, we're not starting with elementary stuff. We're talking about things which I think are going to start you into thinking about probability a little bit. Here's the problem. We have two circles. One is of radius r. The other one is the radius r over 2. Is that okay? We are going to choose a chord through the circle. What's a chord? A chord is any line segment that intersects the large circle. That makes a chord within the circle. You familiar with that terminology? So we choose a chord. We choose a chord at random that intersects the big circle. What is the probability that the length is greater than root 3r? In other words, the length of the chord, as you see here, what is the probability that that's greater than root 3r? Why do we consider root 3r? Well, it turns out that when the chord is tangent to the inner circle, you have to take my word for this unless you want to work it out. When the chord is tangent to the inner circle, the length is exactly root 3r. Is that okay? So what is the probability that the length of the chord is greater than root 3r, which is the length of the chord when the chord is tangent to the inner circle? You with me? That's what we want to figure out. So let's look at some solutions. If this was a multiple choice, let me ask you this. Does anybody have any intuition? Do you think it's a quarter, a third, or 0.5, or all the above?
My guess is 0.5.
Okay, it's 0.5. Well, let's look at different solutions here. Okay, if L is greater than root 3r, then the chord's center is in the middle of the circle, right? If L is greater than root 3r, remember 3r is the length exactly when it's tangent to the circle. But if L is greater than root 3r, then it has to be not tangent to the circle. It has to be such that the center of the chord is within the smaller circle. Do you agree with that? Okay, well, the probability that the length is greater than 3r is the probability that the center point is within the smaller circle divided by the larger circle. And the probability that the point is within the little circle is area of the small circle divided by the area of the big circle. Do you agree with that? And so the area of the small circle is this. Pi r over 2 squared. The big circle, of course, is pi r squared, and that's equal to a quarter. Are we okay with that? So the answer is a quarter, maybe. Let's look at another case. If we have a chord, then it's going to be greater than root 3 over r if the other side of the chord intersects this blue part of the circle. Because if it intersects this blue part of the circle, then it has to go through the middle, doesn't it? Right? Are you following me? In other words, the probability that the length is greater than root 3r is the probability that the other end of the chord goes through this blue circle, or this blue arc, if you will. If it goes through up here, whoop, right, goes through right there, Well, that length is going to be less than root 3r, right? If it goes right here, right tangent to the circle, right, that length is exactly root 3r, right? If it goes through the middle of the circle, then the length is greater than root 3r. So the probability that the length is greater than 3r, or root 3r, is equal to the probability that the other end goes through this blue arc. And of course, the total arc is what? 2 pi r, and the length of this blue arc is 1/3 2 pi r. So the ratio of this arc to the total circumference is 1/3. Are you kind of following? So the probability is 1/3. But wait a minute, we just said it was 1/4.
Can I ask what WLOG stands for?
Oh, that's a good one. Without loss of generality. Okay, thank you. Without loss of generality. We're going to anchor one of the chord's ends. Yeah, thank you for asking. That's probably something which is not apparent. So this is a puzzlement. This analysis says that the probability that it is greater than 1/3, or I'm sorry, that it's greater than root 3r is equal to 1/3. Now, if you're puzzled right now that we got two different answers, yeah, you're right to be puzzled. But let's take even a third example. No matter where the chord is, we can construct a perpendicular bisector, right? No matter where the chord is, this red chord, we can construct a perpendicular bisector. So the probability that it's greater than 3r is the probability that the center of this chord lies on this solid blue line in the middle circle. Because if we have something out here perpendicular to it, that is going to be less than root 3r. If we have the center point within this circle on this tangent line, then it is going to be greater than root 3r. So therefore, the probability of getting greater than root 3r is equal to the ratio of this length to this length. It's the ratio of this shorter line segment to the entire line segment. Well, that's equal to 1/2. Which is a different result than 1/3, which is a different result than 1/4. This is so-called Bertrand's Paradox and was used by the economist. How many have heard of the economist Keynes, Keynesian economics? Yeah, he didn't believe in this idea, and he put up Bertrand's Paradox as one of the reasons that we shouldn't look at this ratio of number of successes divided by the total possible number of outcomes. Remember, that's the classic definition. The total number of successes divided by the total number of outcomes. So here, the total number of successes are all the points on the smaller line. That's the probability. That's the set of all successful outcomes, and over the long line is the set of all outcomes. I don't know if I said that right. The small interval is the set of all successes, and the longer line is the set of all possible outcomes. And so it's 1/2. So if you remember, my original thing is, what's the answer? 0.25, 0.33, 0.50. Well, it looks like it's all of the above. Really, really weird. Now, fortunately, we can resolve paradox. And I'm wondering if anybody has a resolution to the Bertrand Paradox as I presented it.
I don't have a solution, but there is something that concerns me. I wonder, okay, how can I test this experimentally? I think that depending how I model the problem to experiment, I can't get any of the answers. If I model it according to...
Well, you can, exactly.
So experimentally, you can get any of those depending on how you model the process. So,
you know, we're a little bit over time, so let me cut to the end. The problem is in definition of this word. We want to choose a chord at random. And Glauco is exactly right. If you define random one way, you're going to get a half. If you define it another way, you're going to get a third. If you define it another way, you're going to get a half. So therefore, anytime we talk about random, or not always, but many times when we talk about random, we better specify exactly what we mean by random, is what Bertrand's paradox says. Let's go back here. If we chose our randomness by choosing a chord and then choosing an arbitrary perpendicular bisector to it, the answer of 1/2 is going to be right. So if you modeled it by dropping a bisector that went through the origin of the two circles, and then chose a random 90 degree chord, your chances of getting a chord greater than √3r would be equal to 1/2. Over here, if you chose a point in the middle of the circle divided by the total circle and then just drew a line through it, then you would get an answer of 1/4. This is a different way of defining random. And if we go up here, same thing, we're defining random differently. So the solution to Bertrand's paradox is that we got to be careful sometimes in defining exactly what we mean by random. So the problem is not of the definition of random. The problem is not with the classical definition. The problem is defining random. And sometimes we have to be careful of that. Many times it isn't needed. If we talk about getting 3 pips on one throw of a die, that's going to be 1 out of 6. There's no problem there in deciding what is random. Okay? Any questions on that? Okay, well, I think we've gone over. I want you to understand this, okay? Because again, this is really important. This was a profound idea which was presented by Bertrand as a counterexample to the classical definition. Count the number of successes divided by the total number of outcomes as equal to the probability. And as we see, we have to be careful because we have to define what we mean by random. And Bertrand's paradox shows us that. Okay, very interesting results. So what I'd like you to do for a week from today is to solve the Fermat Pascal unfinished problem for the flipping of a fair coin, a 50-50 fair coin. And what happens? How do you divide that pot if you have an unfinished game of 2 versus 1? Let's look at that specific problem. And they had a rough time doing it. You might have a rough time doing it too, but fortunately you have a background in probability and you have all of Google at your disposal. Okay. In fact, let's do this for next time. Is that okay? Can we do this for next time? Give you a running start on what to do.
Dr. Marks,
yes.
on the Google Sheets, there are 2 other things.
I'm going to change those because I didn't get to those today.
Oh, okay.
Yeah, thank you for pointing that out. Yeah, on the Google Sheets, I have to change that. I thought I would get a little bit farther today, but I have a propensity to pontificate, so I went a little bit long. Okay, any other questions? So let's do that for next time. I'm also going to change that on the Google Sheet so that this is going to be required by the 21st. Do you think you can do in 2 days what it took a correspondence between Fermat and Pascal a number of times could not do. They finally did it because they were geniuses. Okay, hearing no protests, let's, yeah, Theo said, yeah, we're standing on the shoulders of great, great people. I mean, you think of the death of Pascal at the age of 39. Just the stuff he did before he was 39 is just astonishing, both in mathematics, science, and Christian apologetics, just astonishing. Okay, if there's nothing, we will see you then on Thursday and talk more about stuff, and I will change the Google Sheets. Take care. Bye-bye.
Guys.
Bye-bye.